Hey there! In this video we're looking again at applications of exponential functions in solving real-world problems that involve growth and decay, except this time we're looking at situations where the period is not 1. So where the rate of change is being applied in something other than 1 unit of time or whatever parameter. So something could be doubling every 10 years or getting cut in half every 3 months or something like that. All right, the first example we're going to look at where the period is something other than 1 is the situation of exponential growth of bacteria. Now, generally bacteria reproduce by binary fission where a bacteria, a single one, divides into 2 in a given amount of time. And we're going to think about a culture here that has 850 bacteria at the start, and they typically divide every 5 hours. Now, again, the big difference is what we're thinking about is the rate that is applied every 5 hours, not every hour. And so the period is 5 hours, not 1 hour. And the rate, if we think about it here, if each bacteria becomes 2, the rate is 2. And that is applied every 5-hour period. So in the table down here, I've got 3 rows this time. First of all, periods. And then secondly, the time in hours, which is pretty straightforward. After 1 period of time, that's 5 hours, right? And it's doubled once then, so we can think about it as it's doubled once, been multiplied by 2 if the rate is 2, and so 850 becomes 1700. After 2 periods, or 10 hours, it becomes double that again, right? And so on, right? 15 hours, doubled again. 6,800, 20 hours, doubled again to 13,600, and then the last one in my table here is 25 hours or 5 periods, doubled again to 27,200. Now we can write a model function for this just like we did in part 1. The only difference is going to be how to take care of the fact that we want the rate to be applied every 5 hours rather than every 1 hour. So I'm going to write a function where I'm using n as the number of bacteria and t as the time in hours. If this were a situation where the quantity was doubling every hour, as you might have had in the first part, then the function would look something like that, right? As we had before. The number of bacteria would be our initial value, 850, and our rate here is 2 because it's doubling, right? And that would be to the power of time in hours. But it's not that it's doubling every hour, it's doubling every 5 hours. Now, if we kept the function like this and say we put in 5 hours here, that would be 2 to the 5th here. It would be multiplying our initial value by 2 5 times, but that's not what we want. We only want it to be multiplied by 2 once. And so how we're going to achieve that is we're going to put a little adjustment in the exponent here. We want it to be doubled every 5 hours, so we want that exponent to be 1 when the time is 5. So all we have to do is divide the time by 5, and that gives us the correct exponent. Right? If you put in a 5, right? So we put in this 5 divided by 5, that's going to be 2 to the 1. If we put in this 10 divided by 5 is 2, and so on, right? So when the period is something other than 1, you're going to have an adjustment to this exponent here. If the period is longer than 1 unit of time, you're going to divide by that period up there. All right? Now we can use that function to work out some missing values. So this next part here, assuming it can keep going and there's no restriction on the growth, how many bacteria might there be after 24 hours? Now to work that out, we can just take our function and use it to determine the value of n when time is 24. And so we can take the function and substitute in 24 for our time and then work it out. You can go to a calculator and work that out, and what you'll find is it's approximately 23,679. Right? Last part of this first example, we can also use it to determine a time that it's going to take to get to some fixed number. So this is when, or how much time will it take before there's 1 million bacteria there. So in this case, it's kind of the reverse. We want to determine the value of t when we're given a value of n, a million. And so we can take the function and substitute in 1,000,000 for our value, our final value. And then we can go about solving it similar to how we have in the past. Just because this exponent is something a little more complicated doesn't matter. We're still going to work to isolate that. It's just we're going to have that 5, and that's going to actually be one of our last steps we take care of. I think the best first step is divide both sides by 850, because then we have this where we can cancel that out, and then what we're going to end up with is that simpler equation there. And now that it's that simpler equation, it's simple enough to just take the logarithm of both sides. And that's going to allow us to use the power rule for logarithms. So we can take that exponent and put it in front. Just because it's t over 5 still works the same as if it was just a t. Can put it in front, and we end up with that equation. And then to go about solving that, we want to isolate that t. So there's just two things we have to take care of there. What we need to do is we need to get rid of the divided by 5 here, which we can multiply both sides by 5. And we also need to get rid of this log 2, so we can divide both sides by log 2. And so what that gives us is an equation that looks like that, right? When it's all said and done, you can work it out on a calculator, and you'll come up with a value of approximately 51.00. That's rounded to 2 decimal places. I know it seems like maybe you don't have to put the 00, but when you write that, you're saying you've given it accurate to a couple of decimal places. But that being said, probably in this situation, you're not interested in the hundredths place or even the tenths place, and we're just going to say that it's about 51 hours. The situation in our second example is a common application of exponential functions where the period is something other than 1, and that is decay of radioactive elements like uranium or plutonium. They spontaneously change their mass to energy and consequently lose some of the mass in a fixed period of time. The fixed period of time that they lose half of their mass is called the half-life of the element. And we're going to look at the specific situation of something called strontium-90, and we're going to consider that we have 400 grams of it to start. And strontium-90 has a half-life of 28.1 years. And so what that means is the amount you have gets cut in half. So the rate is 1/2, or you could write it as 0.5. And that rate is applied every 28.1 year period. So in the table down here, I've got half-lives, or in other words, the period, number of periods, the number of half-lives that have happened. After one half-life, or in other words, after 28.1 years, that amount is going to get cut in half or multiplied by 0.5, so you're going to have 200. After another half-life, 56.2 years, it's going to get cut in half again to 100. And after a third one, 84.3 years, cut in half again, 50. Next one, cut in half again to 25. And the last one in the table here, cut in half, you're down to 12.5 grams of that substance. We can write a function just like we've done already. Our model function is going to look very similar. I am going to use t again for the time in years. I am going to use a for the amount remaining at any point here. You can use whatever letter you want. If you like y and x, please use y and x, but it's probably good to get used to using different variables. In this situation, our model function is going to look similar to our first example. It's going to look like that. Our rate is 1/2 or 0.5, as I said. That's that. And then the exponent up here, the exponent is going to be time divided by that period again, right? And the period is 28.1, so it's on the bottom there. We need to divide by 28.1 to get the right number there. Again, say when you substitute in 28.1 there, 28.1 divided by 28.1 is 1. It gets multiplied by 0.5 once. And if you put 56.2 in there, 56.2 in there divided by that is 2, gets multiplied by 0.5 twice, and so on. All right, so that's our model function. We will use it to find a few values here. In this next part, we're wondering how much is going to be left after 200 years. Well, after 200 years, we only went up to 140 years or so in our table. So it's going to be less than, if you kept going this way, Well, it's going to be less than 12.5 for sure, but we can use our function to find out the exact amount here. So what we want to do is we want to know what's the value of a when the time is 200 years. So we can take our function and substitute in 200 for t, and then just work it out. Go to a calculator and work that out. If you do, you're going to find that you're going to get approximately 2.88 as the value, so that means that we have approximately 2.88 grams of that substance left. The last part of this example is similar to the first one. It's a bit of a reverse here. This we're asked, how long is it going to take until there's only 78 grams left? So what I mean by the reverse is, again, we got to determine a time this time when we're given a final value here. And so we can do what we did in the previous one, is substitute that number in for our final value and then solve for the time there to find out how long it's going to take. To solve that, best first step I think is divide by 400, because again then you cancel that out and you just have on the left side 78 over 400. I'm not actually going to divide that. I'm going to leave it as is for now and just leave it as a fraction until the very end. On the other side, just 0.5 to the t over 28.1. We can take the logarithm of both sides. Allows us to take that exponent and put it in front. And so you have an equation that looks like this. We want to isolate that t, so we got to do a couple of things here. First, I'm going to multiply by 28.1 because then that gets rid of this. And then I have that equation, and now all I have to do is get rid of that. And the way I do that is divide by log 0.5, because again, of course, it cancels that out on that side. And so I can go to my calculator and put that expression in, making sure you use brackets and everything appropriately there as necessary, and you get 66.27, so approximately 66.27 years, however accurate you want it. So maybe before we do our last example, we'll just kind of write a general model function for these situations, now including the fact that the period is not 1. It looks, again, very similar to what you had in part 1. The only difference is in this exponent, we've got divided by p there. And this is, again, where t is the time or other. There are situations that can be examples of exponential growth or decay where the variable involved, there's not time, it's depth or something else. But so I'm going to write time or other. And then the other variables are just the same as in part 1. We had y0 as the initial value. We had r was the rate. But the new thing here is we have p is the period. And then, of course, y is the value after that time. All right? Now, incidentally, if the period is 1, right? If the period is 1, if you put a 1 in here, it just defaults to the equation we had last time, because dividing by 1, you don't need it there. And that was the equation we used in part 1. So it's not really that there's two different things. It's that this accounts for the fact that the period might not be 1. All right, let's do one last example. This is, again, where we're working with half-life. But this time, when you read this problem, it seems like there's a lot less information given. And we're actually going to look at two different approaches to solving this. When you read it, you see that you're given this value of 20% of this certain substance decays in 30 hours, and you're looking for the half-life of the substance. Now, if you think about our model function, there's 5 different variables, so you might be thinking, 5 different variables in my model function, and I'm only given 2 values here. How do I work with that? So I mentioned that we're going to do 2 different approaches to this. The first method we're going to use is we are going to solve for the period, because in our previous example, the half-life was the period. So we're going to set it up where we're solving for the period. So just like in the previous example, we can use a half as the rate. And part of the reason why this seems more difficult is because looks like we're only given one value to do with the amounts here. But if you think about it, a percentage is actually a ratio, a comparison of amounts. So if we think about 20% decays, that means that 100% becomes 80%. And so really we have two values. We can think of the initial amount as 100%, or you could even call it 100 grams, pick a number. And then the final amount, call it 80%, or again, you could call it 100 grams and 80 grams, or 100,000 grams and 80,000 grams. Or the simplest thing to do is call the initial amount 1.00, and that decays to 0.80, because that percentage is the ratio. The other thing that we had was the fact that that took 30 hours to happen. We're dealing with half-life, so we're saying the rate is a half. And then as we said off the top here, we're looking for the period of the thing. So if we write our model function, I am going to use a for amount again, and a0 for initial amount, rt to the power of t over p. If I substitute in the values I actually know both of those numbers, 80 and 100, or 0.8 and 1.0, and then I know that my rate is 0.5 and my exponent is going to be the time of 30, and p is my unknown there, so that's what I'm solving for, the p there. My usual first step was to divide both sides to get rid of this number, but it's a 1. You don't need to divide by 1. Dividing by 1 doesn't do anything, right? If you had called it 180, right? If this said 180, let's imagine this said 80 over here, and there's no decimal place there, 100. The first thing you would do is 100, 80, 100. 80 over 100 is 0.8 anyways. So really, you can just go straight to this without making any change at all. Dividing by 1, you don't need to do. And we have that simpler equation. And then like before, we can take the logarithm of both sides, and we have that as the result after taking our exponent with the power law and putting it in front. And then since we're trying to isolate p, I don't really like it being on the bottom over here. So I'm going to multiply both sides by p, because once we cancel it over there, it's on the top on the other side, which is going to be easier to work with. That leaves us with something that looks like that. And then all I have to do is divide both sides by log of 0.8, because then this cancels out. And so what I have is just a p on the left and 30 times log of 0.5 divided by log of 0.8. And that gives me roughly, if you go to your calculator, 93.1885. So we can say it's approximately 93.19 years. Again, you could say 93.2 years. You could even say roughly 93 years if that's what you want, depending on how accurate you want it. All right. Now I said that was method 1, where we're solving for the period. Now what I mean by solving for the period, you might say, well, isn't that the thing that was missing? You'll see we can do kind of interpret this a slightly different way, set it up, we'll get the same answer. So our second method here is going to be just where we read it and not zero in on, oh, half-life. It must be where we make the rate 0.5 and go from there. Instead, it's looking at this and that giving us our rate instead. So I'm calling the second method solve for time. And the time is just how long does it take till there's half as much. If 20% of the substance disappears, it means that 80% remains. And that happens every 30 hours. And then what we're looking for is how long does it take for our original amount, which is 100%, to turn into half as much, 50%. So if we make a list of what we know and what we're looking for, we can think of our rate as 80%, and that happens every 30 hours. So we can think 80% is our rate, and our period is 30 hours. And we can call our initial amount 100%, and then we're asking how long does it take to get to 50%? Our final amount's 50%, and so the unknown is time. Now, I know that's a different interpretation, but when you go through it, you'll see that it's going to work out just the same. So start with that same thing, except we're going to fill in that function according to the way we just listed those variables. So we're saying our starting amount is 100% or 1, and our final amount is 50% or 0.5. We're saying our rate is 80% right there, and we're saying that happens every 30 hours, so we put the 30 on the bottom there. Now I know that's different, but you'll see that it gets you to the same place. Again, you don't need to divide by 1, you can just get rid of it, and you'll have that equation there. You can take the logarithm of both sides, you can move that to the front over here, and you end up with that equation there. We need to do two things to that, right? We need to multiply by 30 on both sides because that cancels out. And then we need to divide by log of 0.8 on both sides because that cancels out, so that we only have time over there. And then on the other side, 30 log 0.5 divided by log 0.8. If you look, you'll see that's exactly the same expression that we had in our previous method of solving. And that's going to give you what we had before, which was 93.19. All right, so maybe the takeaway from that is that there's more than one approach to solving these problems often. It isn't that there's one correct approach and everything else is incorrect. As long as you're interpreting the problem and the information given appropriately, you can often use multiple different methods. And maybe the second takeaway from that last one is, if you initially look at a problem and it doesn't seem like there's enough information, think about it, especially when percentages are involved. There's more there than you might realize. All right, that's it.